Do I need to speak loudly?
That's fine.
Okay. Thank you for this opportunity to present to you. Bart sends his apologies. He actually just stepped into the doctor's office to have a checkup as to why he's feeling so poorly. I'm going to talk about what the OGC has been doing in terms of 3D, standards for 3D, not just indoor, but also the fact that we are looking at seamless integration of outdoor, indoor models for navigation from outdoor environments to indoor environments and indoor to outdoor environments. Now, we're also concerned about time. And we're also working on some new standards for integrating the Internet of Things into the building environment. And we're also looking at another standard activity for tracking moving features. So I hope by the end of the presentation you'll see that we actually have a range of standards activities in the OGC that are directly applicable to tracking and navigation applications for the indoor environment. One quick slide here. We need to think about the fact that technology has rapidly evolved over the years, especially now in the 3D environment. And things that some of us worked in the 60s were fairly primitive to what we have today. And our 3D environment today, both outdoor and indoor, in terms of our digital ability to deal with digital data, has rapidly evolved and is a result of the merging, fusion, and convergence of many, many different technologies. The same goes with our standards activities. And of course, all of us think of visualization in terms of the end result of what we're doing with all these 3D data. And so let's sort of take a look at the evolution of what we're seeing in outdoor and indoor space. A lot of this has to do with some of the new technologies that we've heard about in previous presentations at this conference. Way back in the early days, much of the geospatial or GIS technologies worked at the country level or city level. But over time, as our ability to collect data improved and the cost of collecting data has been reduced, we're able to collect finer and finer detailed data at smaller and smaller scales. And so we're to the point where we can actually, using today's technologies, collect all the 3D information related to a cluttered desk in an office. I'm not quite sure whose office that is. I hope it's not for you. So at the same time, since the early days of the OGC, our members have worked on a variety of standards related to navigation, 3D visualization, 3D encoding, and data sharing. The earliest work in 3D in the OGC is the geography markup language. The initial work started in 1998 on GML and grew out of the original OGC WebMap testbed in 99, 2000, and GML became an official OGC standard in 2001 with version 2.0. And then version 3.1 is currently an ISO standard and includes many more 3D types than the original version of GML. And then 3.3 is the most current. The reason for showing this slide is that a lot of the current work in terms of content models for sharing urban environment, 3D information, and the current work on IndoorGML is using GML as the encoding standard for that work. At the same time, the OGC members worked in the location services industry looking at standards at the service level for a variety of different application requirements such as geocoding, reverse geocoding, and navigation. And what came out of that work in 2002 was a standard called OpenLS. And OpenLS primarily was 2D, it could work in 3D, and it's designed to allow seamless access across multiple content repositories and service frameworks. And it was designed to also integrate into something called the OMA Mobile Location Platform. And through the late 2000s was widely implemented and very, very popular. More recently, just due to newer technologies, OpenOS isn't as widely implemented as it used to be. And the OGC members are actually looking at potential ways to leverage the current work on outdoor and indoor navigation in 3D and future tracking to upgrade and enhance the older OpenOS interface. These are the interfaces that are supported by OpenOS. It's an API. It's used quite often in back-end server integration environments for enterprise applications. For a time, it was used by groups like Google and Yahoo. It's still supported by Oracle, Esri, Autodesk, and a number of other organizations. The key ones here were the routing, navigation, and what's not shown here is the tracking service. So the members gained a lot of experience by the implementation of this particular suite of service standards. Can everybody hear me still?
Yep.
Yes.
Hello?
Can hear you.
Yeah.
Am I there?
Yeah.
Okay, sorry. Just wanted to make sure. Okay. And this is the diagram of how these standards fit into the broader location services framework as it existed in the early 2000s. And this is an example of a mobile application. And of course, back in the early 2000s, the screen size on cell phone was fairly low, and the footprint was quite small, a lot different from the smartphones that we have today. So here's a timeline of work since OpenOS, and what drove a lot of the subsequent work was the developing relationship between the OGC and the Building Information Modeling Community and Building Smart Alliance, the international branch of Building Information folks. And we formed a CAD GIS domain working group in 2005, which quickly evolved into 3D information management in 2007. One of the initial focus for this group was collaborating with SIG3D in Germany on something called CityGML. The group in Germany have been working for some time on a model and encoding for sharing 3D urban information. And this resulted in the OGC forming a CityGML Standards Working Group, and in 2008, CityGML becoming an OGC standard. In 2009, there was a lot of activity and discussion related to indoor applications and the use of OGC standards. So at the December 2009 meeting at Google, we had a full-day session on indoor location acquisition and modeling and data sharing, floor plan data sharing, applications and requirements. I'll have a little bit more of that. In 2011, 2010, 2011, other OGC activities were initiated, including something called IndoorGML at the time, which is now turned into IndoorGML. And then more recently, additional work in 3D portrayal to define a standard interface for a client being able to request a 3D scene, whether indoor or outdoor, and use a variety of different tools to actually render that 3D visualization on the client. As you probably all know, CityGML is an application-independent Geospatial Information Model and Exchange Format for 3D city models. And it allows you to encode not just the buildings, but also various aspects of the terrain and the dimensions. And one of the key aspects of CityGML is it lets you capture key semantics related to the building. And all of the visualizations on this screen are from data that was shared using CityGML. And CityGML, the work of CityGML has been fairly closely aligned with the work of BIM and things called industry foundation classes, IFCs, and there are a number of tools that let you move data from CityGML to an IFC and from an IFC to CityGML. And there was a lot of interesting things that have been done over the years, looking at integrating existing OGC standards into a variety of different workflows and applications. This one was done by Alexander Ziff's group back in 2010, where they integrated 3D data shared with CityGML, OpenStreetMap, digital terrain models, OpenLS, and the candidate web 3D viewing service to have a workflow for tracking an individual through outdoor to indoor to outdoor to indoor space. Now let's look at IndoorGML. The original work in terms of the OGC was presented at these meetings at Google in 2009, where Professor Joan Lee and Klaus Nagel both gave presentations. One was on indoor spatial awareness by Professor Lee. The other was on IndoorGML, a modeling language for 3D indoor information by Klaus Nagel, who's also been working with developing CityGML and is one of the editors of CityGML. And based on those conversations back in 2009, the members decided, we've done a lot of work for modeling and sharing 3D city information outside the building. We need to look at requirements for sharing indoor 3D information and look at not just the floor plans, but actually look at the semantics and the different layers of information available for the indoor environment. So this led to the formation of an IndoorGML standards working group. And their initial focus was on navigation, the ability to provide 3D information to applications to be merged with sensor information to track assets in the building and to provide navigation information to users within an interior environment. And work in Asia had convinced the group that was dealing with a multi-layered space model, that it's not just a floor plan, but there are different zones. There are many characteristics of an indoor environment that are unique to an indoor environment, like how do you model an elevator? Or how do you model constriction points where wide hallways go into very narrow hallways to exits in the building? So those are some of the issues that they addressed early in development. In 2011, as part of this work, the OGC had an OGC Web Services testbed thread where they looked at indoor-outdoor location and navigation using existing OGC standards. And the idea was to learn much more about how existing standards could be used for navigation in free space for outdoor and indoor, at the same time capture requirements that would feed into the work for the IndoorGML activity. And this is documented in an OGC engineering report. It's publicly available. It's online from the OGC website. So, in 2013, the aim and focus of the OGC IndoorGML activity is to represent and exchange new information that is required to build and operate indoor navigation systems. As I've mentioned, it's not just about the geometry, but is of a model of indoor space. So what do we mean by that? Indoor space is not just walls and floor plans, but there are sensor systems, like there may be Wi-Fi zones, rippage zones. Within many buildings, you have different security zones. Some are low security, no security. Other may be high security. You have fire zones. You have water pressure zones. Many different types of zones inside a building that need to be modeled and are necessary to understand if you're going to provide a very robust navigation and tracking environment in indoor space. At the same time, the IndoorGML community recognizes that they live in a world of many other standards, and so the indoor work is being harmonized as best as possible with ISO activities, such as ISO 19107 spatial schema, which is what GML also uses. Industry foundation classes for modeling indoor environments. We're looking at how you can go from IndoorGML to KML, the relationship between CityGML and IndoorGML, and also requirements for sharing indoor floor plans. That seems to be a really hot area. And all these requirements for deriving, importing, exporting, and sharing between these different standards environments, there's a variety of different applications related to navigation, such as services for handicaps, emergencies, M-counters, electronic e-counters, indoor robots, big one, and indoor location services. Now, one interesting problem we've run into recently, which was discussed just last week in Mumbai, was IndoorGML has a level of detail concept model. It includes footprint data, which is floor plans, image data, so you can have integrated pictures and video into your indoor environment, share using IndoorGML. And then you'll have level 3, which is simple geometry. And then finally, level 4, which is geometric modeling and texture files, which is the same as CityGML. The problem is the first 3 are different from how CityGML actually expresses levels of detail. CityGML has the 4 levels of detail, but they are identical to what is used in BIM and LFC. So after a lot of discussion, the IndoorGML community has decided they need to collaborate with the CityGML community and come up with a common set of definitions for levels of detail and modify IndoorGML to be consistent with CityGML. And these other types such as images and video will have a separate mechanism for sending IndoorGML for those types of data types. And at the same time, they're also looking at other extensions to IndoorGML for other than indoor navigation. And this is simply because the community, based on experience, is asking for additional applications and extensions to IndoorGML already, even though it's not an OGC standard. We're also looking at collaborating with other OGC standard working groups, such as points of interest, moving features. So we're going to have a special coordination meeting at the OGC meetings in March in Washington, D.C. This is their schedule. Originally, they were hoping to be done in 2013, but based on the issues they've encountered with such as levels of detail and also issues related to elevators, stairways, and constriction points, and the topological representation of some of those, they had to move out their final approval date to mid-2014. One of the nice things about IndoorGML, and again, probably one reason it's been delayed a little, is it's actually been implemented in Korea in a number of different cities for a variety of different applications, and they're actually getting real-world input and requirements from these implementations in Korea. Now again, IndoorGML is just one activity that has potential for enhancing indoor navigation and tracking. Another set of activities are related to the use of sensors and integration of sensor feeds and the fusion of sensor information into applications for visualization, analysis, such as navigation in tree space. This is a test bed activity being done in Cambridge, Mass, and Copenhagen, where they're putting sensors on bikes, and as the bikes move through the cities, they're collecting information on particulates and other pollutants in the urban environment, which then gets fed into a data fusion service where they do intense modeling related to dispersion and other characteristics for pollutants in the outdoor space, and then they visualize it in a 3D visualization at a time. Now this is outdoor space, but there's nothing to say that you couldn't mount sensors on indoor assets, whether they're humans or robots, and collect pollutant information in indoor space, which is quite often, as you know, the indoor space is much more polluted than the outdoor space. So test beds and activities and experiments such as these will really drive how we use 3D indoor space information for analytics beyond just pure navigation. And this is one of the renderings for the city of Copenhagen, where they had a full workflow of taking sensor, tens of thousands of sensor inputs, modeling it into for the dispersion of particulates, as well as ozone and carbon monoxide and a few other pollutants. Integrated with OpenStreetMap and modeled in 3D. And they actually went one step further and added force feed where the surface changes over time, showing densities of dispersion. And obviously, this maps very nicely to the indoor space, which is why one of the key IndoorGML use cases, and one that's been tested in Korea, is the integration of sensor information for navigation and tracking, and to make sure that IndoorGML supports the ability to enable applications to fuse real-time sensor information for indoor applications. Another more recent activity in the OGC that also has implications for indoor space is moving features. This particular activity originated out of requirements in Japan for tracking vehicles to better manage the ability to tell vehicles where to go to emergency routes for emergencies. So if there's an earthquake or a tsunami warning, they can quickly send alerts to cell phones for people who are driving and say, if you wish to get away as quickly as possible, follow this route. That's one of the use cases. So moving features is about describing in a standardized way things such as vehicles, pedestrians, airplanes, and ships. And it's the whole idea is to be able to track and provide information to applications that use this information to provide better decision support to the end users. This is definitely a big data problem. We've run simulations in Japan with over 1 million vehicles to see how the interfaces actually work. Now the OGC doesn't do all of this work in isolation. As we all know, 3D and sensors cross-cut many, many different standards organizations. So the OGC has formal arrangements with a range of different groups that are all working in free space, whether it's outdoor or indoor or both, such as the Web3D Consortium, Golden Smart, Golden Special Interest Group, 3D, the Logical Organization. The most recent one that we signed an agreement with is the Small Cell Forum. They look at small sensor systems, indoors and outdoors, for a whole variety of different applications. They're interested in OGC sensor standards and how they integrate into smart buildings and smart cities. So we're hoping that all of these collaborations in general provide a much more robust standards stack for the entire community that wishes to use these indoor and outdoor 3D information. So with that, I thank you for attending this presentation. I hope you found the information useful. And just to finish, this 3D visualization below here is actually a rendering of information that's been encoded and shared using IndoorGML. So you can see that the level of detail can be quite high resolution and give you an excellent presentation of a particular 3D environment. This is done by the City of Seoul as part of their experiments in developing smart cities and sharing 3D indoor information using IndoorGML. So thank you.
Thank you very much.